Here you see the result of using a developable surface versus a non-developable surface for a roof or a floor structure. The surface on the left, this is developable, and you can see it's just acting in simple beam fashion. So the top of this is in compression, the bottom of this is in tension. But you'll notice that from kind of front to back here, the bonds are not being stretched. The molecular bonds are not being stretched at all in this direction, which means that there is strength left in the material that we're not using. Compare that to this non-developable shape here in this slab. So you see that this is concave in multiple directions. So here now we're developing, there is tension along this direction of the slab, and as well as tension along this direction on the top of the slab. Excuse me, I'm sorry. There is compression on the top of the slab. There's tension on the bottom of the slab. In those directions, which means that, again, you're getting more strength out of the slab because you're using more of the molecular bond's ability to resist the force. This is a concrete slab structure developed by Luigi Nervi, and you'll read about him in other places in the textbook. He's famed for some of his concrete structures that span great distances with very, very thin shells. Basically, you're looking at the underside of the slab. This is a slab where anywhere that unstressed material was present, it was replaced, or it was just basically removed, and what remain are the ribs that are necessary for the structural support of the floor. This is a composite that was developed by Luigi Nervi, and he called it ferro cement. But by modern standards, it's nothing exceptional. It's just simply a high compression strength concrete with a wire mesh incorporated. He used this in the development of some of his thin domes, which were quite impressive. They could span distances much greater than the equivalent beam of an equal thickness. So you might have a dome that's got a concrete roof thickness of 3 or maybe even 4 inches, something really small like that, and it's able to span huge distances, 80, 90, 100 feet. Very, very minimal material. And again, it's because we're using this material efficiently. Basically, every bit of material in that dome is stressed. There's no dead weight in the structure. As you can see here, more of Nervi's work, he was quite prolific in his development of materials and construction techniques. This is actually a sailing vessel that is constructed of the ferro cement product. If you go over to the university here in town, you can go to Engineering Hall and you can actually see concrete canoes that the civil engineering students have entered in the concrete canoe competition, and that kind of continues the spirit of this. Basically using a concrete composite of some sort that is reinforced to give the type of strength that you need for a boat hull, that is to say both strong in tension and compression. One of the kind of interesting things you see in some of the concrete canoe devices is that they'll use a very, very lightweight aggregate. And that's basically to reduce the mass of the canoe. That means it needs to displace less water, and for competition purposes it can be paddled through the water more quickly. A common coarse aggregate that's used in that application is styrofoam packing peanuts, because remember that the coarse aggregate's just basically there to provide bulk to the concrete mix, and then the fine aggregate fills in the gaps between the coarse aggregate, and the cement and water forms these chemical bridges between the fine aggregate and kind of cements everything in place. So it's a good application of kind of our modern understanding of material sciences. Again, just an illustration of the importance of geometry and the strength of a material. Remember that the modern automobile is nothing but sheet metal. There is no frame underneath. It's just simply thin metal that's been folded into complex curves that develop the strength. Now, if you think about this paper is being held out like a cantilever. So it's a beam that is secured on one end with a center of mass somewhere out on the unsecured end. And it's a little bit atypical of most beams in that it develops tension on the top and compression on the bottom. Well, think about this paper as it's just held as a sheet. If we were to zoom in here and look like with a microscope, you'd see the edge of the sheet of the paper. And it's in a cantilever arrangement, so the bottom's under compression, the top's under tension, and in the middle here's the neutral axis. Well, remember that the extent to which the top is stretched and the bottom is compressed is proportionate to this distance from the neutral axis out to these, remember we call those things out at the far edges the extreme fibers. But this entire distance for this piece of paper is, less than 1/1000th of an inch, which means that the side of the paper that's getting stretched and the side of the paper that's getting compressed, the strain is so small that the paper's really not able to develop any resistance to that. Comparing that to this complex curve, look at how far apart now our extreme fibers are. We're probably looking at extreme fiber distances of maybe 2 inches here. Well, what does that mean? That means that if you're going to load this thing like this, this top part of this curve here has to get either substantially longer, or this bottom part of the curve here has to get substantially shorter. So we've generated large strains that develop large forces to resist the load. Incidentally, this is kind of a good illustration of slender structures. We know that we're not likely to tear this paper, right? It's not real likely that we're going to develop tensile cracks in the top of this. What's far more likely is that we're going to have a buckling type failure down here on the bottom, which is a characteristic of slender structures, and we'll talk about that some more when we look at Euler's columns, which was a prediction of, he predicted basically that columns would fail in buckling once they got sufficiently long and spindly. Here you see an application of that curve structure to create some geometry to separate the extreme fibers of the material used in a stadium roof. And so this is a reinforced concrete structure that just kind of illustrates how strength can be gained by moving away from the flat sheet and into some type of a curved or folded structure. This is an arch structure, and this is kind of a classical structure in terms of span. It's one of the oldest span structures there are. And you'll notice that if the sheet of paper is simply set flat across the top of these books, there is no resistance to it developing this curved shape other than the fact that the top of the paper is under compression and the bottom's under tension. But in this case, that effective distance is so short, the strains are so small, it has very little resistance. If, on the other hand, this sheet of paper is put in an arched configuration, now the full sheet, top and bottom, are under compression. They're developing this outward thrust, trying to push these books apart. But, of course, these books have some center of mass, which is not right at the edge of the book. It's in the center of the book, which means that if this book is going to roll this way, it's going to have to pivot about this point, and if this book is going to roll this way, it's going to have to pivot about this point. And in both of those cases, that's going to require lifting the center of the mass of the book. The result is that these books are able, at least to some extent, to resist that outward thrust and prop up this arch. Now, in actual construction, you'll see this done, and some examples are like at Tenney Park, close to the college here. There is an arched bridge that crosses the lagoon, and if you were to look at it, on the ends of the arched bridge, there are earthen embankments. And the purpose of these earthen embankments is just simply to provide something heavy to resist the outward thrust produced by the arch. You'll read about other things in the textbook, such as flying buttresses. That's another approach used in kind of classical construction to try and resist this outward thrust of the arch. The moral of the story here is that if you can create an arch or a dome, you can get all of the material acting in compression, which is a more efficient way to use it than to have some of the material in compression and some in tension. Because remember, when we mix the two, we always get that neutral axis where some of the material is not carrying any of the weight. This slide and the next slide refer to two non-developable surfaces and the directions of the curve. And the first one's familiar, it's a dome. And one of the things you notice is that if you, for instance, were to set a marble on the top of this dome and let it go, you may not know which direction it's going to head, but in any place, it's always going to move away from that center. The curvature is always down in this type of structure. Compare that with the saddle. This is a shape that is occasionally used in modern architecture, and depending on where you set the marble, you may get different results. For instance, if you set the marble along this line here, where there is no curvature, it has no desire to move because it's flat. If you set the marble up here, it will actually roll back towards the center of the saddle. And, you know, or if you set it up here, same thing. Once it got past the center point, then it will roll down towards the ground. So the saddle is an interesting shape because it combines a number of curvatures, and it's an efficient shape because we're able to use all of the characteristics of the material: strength and compression, strength and tension, and again, it's a non-developable shape. So typically these would be constructed of cast concrete, which is an effective way to produce a complex shape like this. Again, here's a developable shape, just an arch, and you'll notice that the difference between an arch and a saddle and a dome is that a dome, all of the curvatures are down. In an arch, all of the curvatures are down with the exception of you have one, if you run a parallel to the arch, you have a no curvature line. And then in a saddle, you have all three. You have downward curvature, upward curvature, and lines of no curvature. Again, not as efficient as the saddle or the dome in its use of materials because it's a developable shape. Here you see an application of multiple developable shapes. You have this barrel roof on this structure. And despite the fact that it's a developable shape, this is somewhat robust because if we think about applying a uniform load to all of these, like perhaps we put snow on this roof, all of these arches are going to want to slide out. So they're all going to develop an outward thrust. The upshot is that with the exception of the end arches, they are all generating thrust against each other. So that if I look at, for instance, this column here, that lateral thrust is localized. There is an action and equal reaction right here created by the roof. What that means is that this column does not really need to be robust at all against lateral thrust loads. Now, when you get to the end, you do have to have some resistance to lateral thrust loads because there's not another arch here creating a reaction. So you have to have, for instance, a tensile member running across the end of this last vault here to ensure that this does not slide out. But overall, it's a pretty efficient way to span a long distance. And you know, this is essentially reproducible to any scale. You could just continue to add arches without limit, pretty much. And you could continue to extrude these arches out in this direction without limit. So that if you're able to live with the occasional support on these vaults, you can cover a very, very large area with a pretty simple roof structure. Here you have a slide that illustrates kind of the compound action of the barrel roof. If it's supported on its flanks, it acts like an arch and produces thrust outward, like we talked about in the last slide. If it's supported on its ends, it acts like a beam, and it's going to act in bending, compression on the top and tension on the bottom. Of course, if it's supported on both sides, you get both of these actions, and it's kind of akin to the floor slabs that we looked at, where you're able to produce deflections in two directions, use more of the strength of the material to your advantage. This is called a folded plate roof, and you've probably seen this many times before in many different demonstrations. Local examples of this type of roof would be the Alliant Energy Center. The Coliseum itself actually has this kind of corrugated folded roof, which produces greater strength than if it were a simple dome. Of course, the other application, kind of the consumer product application of this, is in the use of cardboard. If you think about why this works, what we've been able to do is take this thin sheet and push the extreme fibers further apart. So you got to imagine that this is spanning some direction kind of off screen like that, and it's going to take on a sag, which is going to mean that these top extreme fibers are in compression, the bottom extreme fibers are in tension. The neutral axis is going to run right through mid-height on this. So again, this material, mid-height, is not carrying a lot of weight, but if you look at the design where the designers have put most of the material, it's in the top and in the bottom of the structure. Again, it's just one of those things that kind of arises out of understanding that as goes the strain, so goes the stress. You try to put the material where it's going to be deflected the most so that it can carry the most of the load.